Well, hi everyone, this is Bob the Science Guy, and today we're going to talk about one of my favorite subjects, flight instruments, specifically the attitude indicator. Now, a very common argument that you will hear in the flat Earth is that in order to fly around the Earth, planes would have to dip their nose to fly around the globe. But that can't be done because if you look at the data from the flight instruments, specifically the gyroscopic attitude indicator, which is rigid in space, it shows that the plane does not dip its nose at all. Therefore, the Earth must be flat. Well, is this actually the case? Well, no, it's not, because flight instruments are not gyroscopes. They are not rigid in space. They are instruments that are gyroscopically stabilized, but in many cases they're self-correcting. For example, while the heading indicator, which matches your compass heading, is a gyroscopically stabilized instrument, it does not self-correct. And as a result, we have to manually change it every 15 or 20 minutes as we fly over the globe Earth. However, the attitude indicator, which is also a gyroscopically stabilized instrument, does self-correct. And it self-corrects to the vector of gravity, which is down. And as a result, as it flies over the globe, it's constantly adjusting what down is and maintaining a particular attitude in relationship to that changing down. Now, to give you an exact idea of what I'm talking about, look at this drafting square. Notice that the top of this drafting square is 90 degrees to the long edge of the drafting square. So, if we look at this as the vector of gravity, if we simply rotate it like so, even though this is now a new down compared to when it was over here, this is a new direction for down, it's still at a 90-degree angle to that down. So as the aircraft flies over the curved surface of the Earth, down is constantly being adjusted to be the line between the aircraft and the center of the Earth. And that changes as it flies over the curve. So the angle that the attitude indicator is reading will not change, even though the downward vector is changing. So let's go ahead and have a look at an actual attitude indicator. Now this is the attitude indicator that we're going to be using, the R.C. Allen. Notice there's a couple of features to it. First of all, this little kind of W-shaped feature here, it represents the aircraft. So that would be the left or the port wing. This is the right or the starboard wing. This is the center line of the aircraft. The blue is up, the brown is down. Where the blue meets the brown is the horizon. This is your bank indicator. This little red tag right here means that this unit is not powered up and functioning. When it is powered up and functioning, that will go away. And down here, we have a little knob that we can pull to cage the attitude indicator, which means hold it where it is. Now, obviously, this is a rather expensive piece of gear. I don't have one, but my friend Wolfie6020, who is a corporate pilot based out of Australia, does. And he did a series of videos on his attitude indicator a few years ago and has graciously given me permission to use some of his footage. Now, the first thing that I want to point out is this is the same attitude indicator that we looked at a moment ago. You have the model number and you can look up the specs on it if you wish. It is an electrically powered gyroscopic attitude indicator. Now, he's getting ready to go ahead and hook up the power supply to this. Notice the red off flag is showing, which indicates that the gyro is not spinning. The thing that I want to point out is notice that the airplane is not level with the horizon. Although the dot in the center is on the horizon, you see that that left or port wing is high and the right or starboard wing is low. Watch what happens when he powers up the gyroscope.
You can see that the off flag has disappeared. You can probably hear the gyro spinning up, and you'll see that it will slowly align itself to level.
Now notice that the attitude indicator now indicates that that table is in level flight, even though it didn't start off in level flight when he spun up the gyro. Now the question becomes, if a gyro is rigid in space, why didn't it stay at the original position once the gyro was spun up? It's because it's not rigid in space. It's gyroscopically stabilized, and it responds and self-corrects to what the downward vector of gravity is. And to do that, it uses something called pendulous vanes, which we'll discuss further in a minute. As has been pointed out, some of the early attitude indicators did not have pendulous vanes, and that is correct. The earliest attitude indicator was a mason jar half filled with motor oil to kind of give you an idea of what the direction of down was. We then went to gyroscopically stabilized attitude indicators, much like the current heading indicators that we have now. However, they had to be periodically readjusted due to gyroscopic precession as we went over the surface of the Earth. Modern attitude indicators have pendulous vanes and correct automatically to the vector of gravity. Now next we're going to demonstrate this auto-correction. So I'm going to turn it back over to Wolfie and let him take it from here.
So the gyro is now aligned nicely, and what we're going to do is the first demonstration where I will deliberately put the gyro out by 20 degrees and we can time how long it takes to self-correct. And let me just show you first that the gyro is actually working. If I move the case, the gyro inside the artificial horizon is holding level nicely. If the aircraft were to pitch up, that's the indication you get. If the aircraft pitches down, that's the indication you get. The aircraft is banking to the right. It looks like that. The right wing is low. If it's banking to the left wing is low. So the artificial horizon is functioning correctly. So now what we're going to do is cage the gyro. I'm going to rotate about 20 degrees to the right. I'm going to release the cage and then put the case back, and you'll see it's just a little bit more than 20 degrees misaligned now. So I'm going to start the stopwatch and we'll see how long it takes for the gyro to erect itself back to level.
Now one thing that I do want to point out here is that the gyroscopically stabilized attitude indicator is running, the gyro is spinning, and the horizon is tilted off to the right, as you can see, because the plane, according to this, is in a left bank. Now notice that it stays there because it's gyroscopically stabilized. Now if it was rigid in space, it would remain right here. But let's see what happens. Now one thing I want to point out is that if this was rigid in space, it would maintain this attitude indication no matter how much time went by. The pendulous vanes will correct this by reading the vector of gravity and bring it back to level over time because it's gyroscopically stabilized, not rigid in space.
Now, as you can see, it is definitely in the process of realigning itself. It's only been going for less than 2 minutes, and it has already corrected by more than a couple of degrees. Just to explain, this is the vertical position. The first white mark is 10 degrees bank. The second one is 20 degrees bank. And the third one there is 30 degrees bank. The little white dot is 45 degrees bank, and the next white line is 60 degrees bank. So when I deliberately offset the gyro, it was just more than 20 degrees, and you can see now it has reduced to about 17 degrees angle of bank in just 2 minutes. So it's definitely correcting itself much faster than 1 degree every 8 minutes. We'll just let it run until it's completely wings level again, and then we'll repeat the experiment, rotating it in the opposite direction.
Now, the reason he's discussing 1 degree every 8 minutes is that a jet aircraft will cross 1 degree of latitude in about 8 minutes. And as it flies over the curve of the Earth, the question becomes, will it correct fast enough to compensate for the curvature of the Earth without having to dip its nose down? And quite frankly, the answer is yes, because we're going to see how long it takes to compensate for more than 20 degrees here in a moment, and I suspect it will be less than 80 minutes. So if you do a little bit of math, in 4 minutes, it's corrected more than 10 degrees, which means that it corrects at least 20 times faster than is required when flying over the Earth in an actual aircraft. Now, skeptics may ask, why is it taking so long? Well, one of the beauties of gyroscopic stabilization is that it maintains its position in space during short-term maneuvering. So say you make a bank or you climb, you don't necessarily want the attitude indicator to immediately reset. You want it to have a little bit of persistence at the current rate of level. But as you go over the surface of the Earth 1 degree every 8 minutes or so, you do want to have it correct at that rate.
You can see now the artificial horizon is showing just 10 degrees angle of bank, so it has already corrected more than 10 degrees in just 5 minutes. Remember, it only needs to correct 1 degree in 8 minutes to be able to compensate quite easily for the movement across the Earth's curvature in a jet aircraft. This is correcting much faster. It has corrected more than 10 degrees in just 5 minutes.
Again, if this was rigid in space, we wouldn't see any correction at all. It would simply maintain its original position due to gyroscopic rigidity. But again, this is not rigid in space. It's gyroscopically stabilized and self-correcting due to the pendulous vanes, and you're seeing those in action right now. And again, this is all in real time.
So there's the 8-minute mark. The artificial horizon is now showing about 5 degrees angle of bank, which means in 8 minutes it has corrected more than 15 degrees of error. Now that is far more capable than what is needed just to correct 1 degree every 8 minutes. In fact, this humble little gyroscope out of a helicopter would function perfectly on something travelling as fast as the SR-71. It's correcting fast enough to easily compensate for the curvature of the Earth, even in an aircraft that fast. This time we're going to offset the angle in the other direction, just to confirm that it wasn't a fluke in pitch. So what we're going to do is just cage the gyro. We're then going to pitch the aircraft upwards by about 10 degrees. I will release the cage and then lower the attitude. So that's now indicating about 10 degrees nose down. And if we start the stopwatch, let's see how long it takes for this gyro to correct back to level. Remember, it only needs to correct 1 degree in 8 minutes for an aircraft travelling at 450 knots. So let's see how long it takes to correct 10 degrees.
This would be the correction needed as we had to quote-unquote dip our nose as we went around the curve. About 1 degree every 8 minutes. I want to remind everyone that 10 degrees downward dipping of the nose as we went around the curve represents more than 600 nautical miles. And to fly that in a commercial jet at 450 miles an hour would be about an hour and 20 minutes. So as long as this can correct that 10 degrees in less than an hour and 20 minutes, it would easily keep up with the curvature of the Earth and read level flight. Recall, if this was rigid in space, the attitude indicator would maintain this reading no matter how much time went by. Look at that, 3 minutes and it's almost all the way back to level flight. Just a couple of degrees to go. This is the pendulous vanes reading the vector of gravity and establishing what down is at the location of the attitude indicator. So once again, we have to accomplish this correction in 1 hour and 20 minutes to maintain level flight over a curved Earth, and we're almost there in 4.5 minutes.
So there you can see in just 5 minutes it has corrected itself back to the level attitude. So it's easily correcting 10 degrees in 8 minutes. It only has to correct 1 degree in 8 minutes. And in case you're wondering why it's not showing perfectly wings level, it's because this table is not perfectly level. And just to prove that, I've put a small bubble level on top of the artificial horizon, and you can see that the bubble is just there. So the body of the artificial horizon is not perfectly level there, and that accounts for that very slight angular difference. If I just tilt it so that the bubble level is level, the bubble level is level now, you can see the wings are perfectly level also.
So, just to sum this up, it's very obvious that a gyroscopic attitude indicator is simply gyroscopically stabilized. It's not rigid in space. It is self-correcting to the vector of gravity. So as the direction of down changes as we go over the curved surface of the Earth, the attitude indicator easily corrects for that and maintains level flight. So, this is Bob the Science Guy. In our next episode, we'll talk a little bit about how this actually occurs using something called pendulous vanes. And once again, thanks to Wolfie6020. Make sure you give him a follow. Check out his videos. He's got an entire playlist on this, and I'll put a link to it in the description of this video. Take care, guys.